In this video, we're going to look at how to simplify square roots. To do this, we'll use the product rule for radicals, which says that anytime we take the root of a product of two factors, that's the same as taking the root of each factor separately and then taking the product. Remember that this does not work if you have addition or subtraction inside. You cannot split up the root with addition or subtraction, only with multiplication or division. Here's an example. We're asked to simplify the square root of 45. And 45 is not a perfect square, so this square root will not be equal to a nice whole number. But if there are any perfect square factors in this number, then we can write it as a product of the two factors and then take the square root of each of those factors separately. So we can simplify this by factoring out any perfect square factors. Here are some of the perfect square factors that we'll be looking for. 2 squared is equal to 4, 3 squared is equal to 9, 4 squared is equal to 16, and so on. We'll want to find the largest perfect square that divides evenly into 45. It's not difficult to see that 9 is the only number in this list that divides evenly into 45. So we rewrite 45 as the product 9 times 5. And now we can rewrite this using the product rule by taking the square root of each of the two factors separately. And now, since we factored out a perfect square, we can simplify this square root. The square root of 9 is equal to 3. And that gives us that the square root of 45 is equal to 3 times the square root of 5. And since the 5 that's left inside the square root does not have any other perfect square factors, there are no other numbers in this list that divide evenly into 5. That means we cannot simplify this any further. This is the simplified form for the square root of 45. Here's another example. We're going to simplify the square root of 72. We want to see if any of these perfect squares divide evenly into 72. And you can use a calculator for this if you need to. You'll divide 72 by each of these perfect squares and see if any of them divide evenly. We'll find that 4 divides evenly into 72, and so does 9. But if we keep going through this list, the largest perfect square that divides evenly into 72 is 36. 72 divided by 36 is equal to 2. And that means that we can write 72 as the product 36 times 2. And now we can use the product rule for radicals and take the square root of each of these factors separately. So we get the square root of 36 times the square root of 2, and that simplifies to 6 times the square root of 2. Notice that here we used the largest perfect square factor of 72, so we were able to do this in one step. Let's see what would happen if we had used one of the smaller perfect square factors. Suppose, for example, that you started with the perfect square factor of 9 and wrote 72 as the product of 9 times 8. Again, we can take the square root of each of these factors separately, and the square root of 9 is equal to 3, so we get 3 times the square root of 8. This, however, is not completely simplified. 8 is divisible by 4, so now we can factor out another perfect square factor. Rewriting 8 as the product of 4 times 2, we can now split up the square root again between these two factors. The square root of 4 is equal to 2, so now we have 3 times 2 times the square root of 2, which is equal to 6 times the square root of 2. So you can see that it's faster if we start with the largest square root factor from this list. But what's important to remember is that anytime you factor out a perfect square factor, make sure that you check that what's left inside the square root cannot be simplified any further, that there are no other perfect square factors that divide this number. If there are, then you need to keep going until it's completely simplified. Let me show you an alternative method that can be used to simplify these square roots using factor trees and prime factorizations. Remember, to make a factor tree, We can start with any product of factors that equals the given number. I'm going to start with the smallest factors. 45 is equal to 3 times 15. 15 is equal to 3 times 5. And 3 and 5 are both prime factors, so all of the branches are complete now. And that gives us the prime factorization for 45. 3 times 3 times 5. And now when we look for perfect square factors, we'll be looking for a pair of common factors. 3 times 3 is the perfect square 9. And we know that the square root of 9 is equal to 3. So when this perfect square comes out of the square root, the pair of 3's will become a single 3. So writing the number as a product of prime factors just gives us another way of finding these perfect square factors. For small numbers like 45, this method really isn't much easier. But it might be helpful when we have larger numbers inside the square root and when we include variables. 72 is divisible by 2. 36 is also divisible by 2. 18 is divisible by 2. And 9 is divisible by 3. And now we have all prime factors at the end of these branches, so our prime factorization will be 2 times 2 times 2 times 3 times 3. Now we want to circle any pair of common factors. We have a pair of 2's and we have a pair of 3's. So you can see that we have a perfect square factor of 2 times 2 equals 4. And when we pull that outside of the square root, it will become a single factor of 2. And we also have a perfect square factor of 3 times 3, which is equal to 9. And when we pull that outside of the square root, we'll get the single factor of 3. So here the square root of 4 is equal to 2 on the outside of the square root, and the square root of 9 is equal to 3. And we have a factor of 2 left inside the square root. And this gives us the same answer, 6 times the square root of 2. Let's see how this works with variables. In this example, we're asked to simplify the square root of x to the 6th power times y to the 5th power. We're also told to assume that the variables are non-negative. That means that they take values that are greater than or equal to 0. And we'll explain why we include this condition at the end of the lecture. Let's start with the alternative method for simplifying the square root. We won't need a factor tree to write these variables as a product. X to the 6th power is just a product of x 6 times, and y to the 5th power is a product of y 5 times. Now let's identify the pairs of common factors. You can see that we get 3 pairs of the factor x and 2 pairs of the factor y, and there's 1 factor of y left over. And each of these pairs of factors will be a perfect square from our original expression. So when we take the square root of each of these perfect squares, we will get just a single factor of x and a single factor of y. That gives us that the square root of x squared is equal to x, and we get 3 of those products, and the square root of y squared is equal to y, and we get 2 of those. And remember, there was 1 factor of y left inside the square root. So this expression simplifies to x to the 3rd power times y to the 2nd power times the square root of y. This method works nicely. It's easy to use, as long as the exponents on the variable are not too large. If we have a large exponent, like x to the 31 power, we wouldn't want to have to write out 31 factors of x in this product. So let's see if we can find a shortcut for this. Let's compare the square roots of x to the 6th and y to the 5th from the original expression. First, notice that x to the 6th power must be a perfect square, because there are no factors of x left inside the square root after we simplify. Y to the 5th power is not a perfect square because there is a factor of y left inside the square root. And the difference between these two is that x has an even exponent, it's a multiple of 2, and y has an odd exponent, it is not a multiple of 2. First, let's look at why an even exponent, an exponent that is a multiple of 2, will give us a perfect square. To write this as a perfect square, we need to have something raised to the second power. And if you remember your rules for exponents, if we have something raised to a power and all of that raised to another power, we multiply the two exponents. So what exponent would we need here on the inside so that we get a product of that number times 2 equal to 6? That will have to be an exponent of 3 on the inside. X to the third power, all raised to the second power, is equal to x to the 3 times 2 power, or x to the 6th. So here you can see that if this can be written as a perfect square, then the exponent must be a multiple of 2. You can also see that the square root of x to the 6th power must be this expression inside the parentheses, the expression that's being squared here. So the square root of x to the 6th is x to the 3rd. And this is exactly the square root that we got when we used the alternative method here. And the shortcut for taking the square root of a variable raised to a power is to divide that exponent by 2. But we'll only be able to do this if the original exponent is a multiple of 2. If it's not, like the second factor here, y to the 5th power, then we'll have to factor out one of the variable factors first. So y to the 5th power cannot be written as a perfect square as we could with x to the 6th power. In this case, when we want to take the square root, we'll factor out one factor of y. That will give us y to the 4th power times y. When we multiply y to the 4th times y to the 1, we add the exponents to get y to the 5th. So anytime we start with an odd exponent, if we factor out a single factor of that variable, we will be left with an even exponent, exactly one less than the one we started with. That means we'll have a perfect square of y to the 4th power, but we will also have an extra factor of y that will be left inside the square root. Using our shortcut, the square root of y to the 4th power is equal to y to the 4 divided by 2, or y to the 2nd power, and we have the y left inside the square root. So we get y squared times the square root of y. And notice again that this is exactly what we got when we simplified the square root using the alternative method. So if we go back to the original expression and we use this shortcut, we first identify any variables that have exponents that are multiples of 2, so x to the 6th, and any variable that has an exponent that's not a multiple of 2, we factor out one of those variable factors, and we're left with an exponent that is a multiple of 2. And now we can simplify by taking the square root of each of these perfect squares separately, and we'll be left with a y on the inside. Remember the shortcut, when we take the square root, is to divide the exponent by 2. So on the outside, x will have an exponent equal to 6 divided by 2, which is 3, and y will have an exponent of 4 divided by 2, which is equal to 2. And this expression is exactly the same as what we got using the alternative method. Either of these methods are fine, but as I mentioned, if you happen to have a really large exponent on one or both of the variables, then the shortcut will be much faster. Here's an example where we have variables with large exponents. So the alternative method would not be the best choice for this problem. Let's try the shortcut. remember that we want variables with exponents that are multiples of 2. b to the 34th power is a perfect square because its exponent is a multiple of 2. a to the 29th power is not a perfect square because its exponent is not a multiple of 2. And that means we'll have to factor out one factor of a. A to the 28th power times a to the 1 power is equal to a to the 29th power. That gives us the perfect square a to the 28th power and b to the 34th power. And when we take the square roots, we will divide these exponents by 2. And that gives us a to the 14th power times b to the 17th power on the outside, and we have a factor of a left on the inside.